is going to organizing the webinar on the theme present scenario of material science in association with the Luminescence Society of India. On the behalf of Department of Physics, I heartily welcome to the Honorable Nilkantralji Sindhe is going to organize XMLA the and the secretary webinar of the Bhadravati Shikshan on the theme present scenario of material science Bhadravati Shikshan Sanstha in association with I heartily also the Luminescence Society of India. The Dr. on the behalf of Department of Physics, Joint Secretary I heartily welcome to the Honorable Bhadravati Nilkantralji Sindhe is going to organize XMLA the and the secretary webinar of the Bhadravati Shikshan the theme present scenario of material science in association with I heartily also the Luminescence Society of India. The Dr. on the behalf of the Department of Physics, Joint Secretary I heartily welcome to the Honorable Bhadravati Nilkantralji Sindhe is going to organize XMLA the and the secretary webinar of the Bhadravati Shikshan the theme present scenario of material science in association with I heartily also the Luminescence Society of India. Dr. on the behalf of the Department of Physics, Joint Secretary I heartily welcome to the Honorable Bhadravati Nilkantralji Sindhe is going to organize XMLA the secretary webinar of the Bhadravati Shikshan the theme present scenario of material science in association with I heartily also the Luminescence Society of India. Dr. on the behalf of the Department of Physics, Joint Secretary I heartily welcome to the Honorable Bhadravati Nilkantralji Sindhe is going to organize XMLA the secretary webinar of the Bhadravati Shikshan the theme present scenario of material science in association with I heartly also the Luminescence Society of India. Dr. on the behalf of the Department of Physics, Joint Secretary I heartily welcome to the Honorable Bhadravati Nilkantralji Sindhe is going to organize XMLA the secretary webinar of the Bhadravati Shikshan the theme material science.
Good morning, ladies and gentlemen, my colleagues, friends, dear students. At the outset, I take the privilege of welcoming you all in this one-day international webinar on present scenario of material science 2020. Our college, Nilkantrao Shinde Science and Arts College, Bhadravati, especially Department of Physics, is the host of this webinar is aiming to take the name of this college still higher by offering our best possible service to its people in the field of material science in this pandemic situation. I would like to inform this online August gathering that this is the third big event being hosted by this college within the span of 6 months. Especially Department of Physics is the host of this webinar is aiming to take the name of this college still higher by offering our best possible service to its people in the field of material science in this pandemic situation. I would like to inform this online August gathering. I would like to take this opportunity. This is the third big event all being hosted by this college within the span of Bhadravati, especially Department of Physics. The host of this webinar is aiming to take the name of this college still higher by offering our best possible service to its people in the field of material science in this pandemic situation. I would like to inform this online August gathering. I would like to take this is the third big event all being hosted by this college within the span of Bhadravati, especially Department of Physics. The host of this webinar is aiming to take the name of this college still higher by offering our best possible service to its people in the field of material science in this pandemic situation. I would like to inform this online August gathering. I would like to take this is the third big event all being hosted by this college within the span of Bhadravati, especially Department of Physics. Thank you very much. Please do my Thank you, Dr. Sarki.
Are your very valuable speech of introduction speech is very valuable. Now I invite Dr. V.V. Shinde, Joint Secretary of Bhadravati Shikshan Sanstha Bhadravati and the member of the Management Council Gadchiroli for their inauguration speech.
Good morning, everybody. Am I audible?
Yes, sir.
Teachers, researchers, and my dear friends. It's indeed a pleasure for me to welcome you all to this international webinar on behalf of Bhadravati Shiksha Sanstha Bhadravati and Ludhiana University. Dear friends, in this COVID era, we learned many things. For example, how to learn new things in a newer way. We are all doing the things which we haven't done ever before. The how to use innovative methods in teaching as well as in research purposes, and so on and so forth. I see this phase of life as an opportunity for the betterment of ourselves. Physics department of our college always been a forerunner and a torchbearer in implementing and executing newer concepts. This conference is also a brainchild of our principal, Dr. Ladke sir, and each and every faculty of physics department. I congratulate them and wish them best of luck for the success and fruitfulness of this conference. And I'm confident that it will be helpful and definitely will add to the knowledge of participants and will set an example for other departments as well, also to come forward and be a part of mainstream and organize such events. Once again, I thank everybody for calling me and giving me honor, and I wish them best of luck. Thank you. And I'm confident
Thank you very much, sir.
that it will be helpful
Now I
and
invite
definitely will add to the knowledge of
the chairman of
participants
this inauguration function
and will set an
and the
example for
principal
other
of this college,
departments as well,
Dr.
also to come
respected
forward
Dr.
and be
Ladke
a
sir.
part of mainstream
Dr.
and
Ladke sir
organize
is the
such
chairman
events.
of Board of Study.
Once again, I
He also
thank
the member of the
everybody
Senate.
for
He is
calling
the
me
member
and
of
giving
the
me honor,
academical council.
and I wish
He
them
also the
best of
member
luck.
of board
Thank
of
you.
examination.
And I'm
Thank
confident
you very much, sir.
that it will
And
be
evaluation
helpful
of
and definitely will add to the
evaluation
knowledge of
Gondwana University
participants
Gadchiroli
inauguration function and set an
and
example
the
for
principal
other
of this college,
departments as well,
Dr.
also to come
respected
forward
Dr.
and be
Ladke
a
sir.
part of mainstream
Dr.
and
Ladke sir
organize
is the
such
chairman
events.
of Board of
Once
Study.
again, I
He also
thank
the member of the
everybody
Senate.
for
He is
calling
the
me
member
and
of the
giving me honor,
academical council.
and I wish
He
them
also
best
the
of
member
luck.
of board
Thank
of
you. And I'm
examination.
confident
Thank you very much, sir.
that it will
And
be
evaluation
helpful
of
and definitely will add to the
evaluation
knowledge of
Gondwana University Gadchiroli
inauguration function and set an
and the
example for
principal
other
of this. Sir, we start the
departments
welcome speech. Dr. Ladke sir.
Dr. Ladke sir of mainstream.
Dr. Ladke sir is the chairman of Board of Study.
Once again, I
He also
thank
the member of the
everybody
Senate.
for
He is the
calling me
member
and
of the
giving me honor,
academical council.
and I wish
He
them
also
best
the
of
member
luck.
of board
Thank
of
you. And I'm
examination. Thank you
confident
very much, sir.
that it will
And
be
evaluation
helpful
of
and definitely will add to the
evaluation
knowledge of
Gondwana University Gadchiroli
inauguration function and set an
and the
example
principal of. Sir, we start the welcome speech. Dr. Ladke sir. Sir, sir, we start. Sir, switch off the mic. Switch on, sir. Sir, you are not audible. Huh.
May I audible?
Yes, sir. Yes, sir.
Yeah. Very good morning to you all.
Sir, we start the
Chief Patron of this institution and this webinar, Honorable Venkataraoji Shinde, Founder Secretary of Bhadravati Shikshan Sanstha Bhadravati and ex-MLA and President of Bhadravati Shikshan Sanstha Bhadravati, Sau Nilimata Yan Shinde. Respected inaugurator of this inaugural function of this webinar, Dr. Vivek Yan Shinde, Joint Secretary of Bhadravati Shikshan Sanstha Bhadravati and Management Counselor of Gondwana University, Gadchiroli. Dr. Elias Emeka America from Nigeria, a resource person, and second resource person, Dr. V. Natarajan, ex-scientist of Ava Atomic Research Center. My guru, Dr. N.S. Kokode, principal of Yojabai Hitkarni College, Brahmapuri, and my friend, Dr. I.S. Morle, registrar of Gondwana University, Gadchiroli, originally a man of physics. Organizing secretary of this webinar, Dr. Karthik N. Sinde and Dr. Vishal N. Sinde, member of Bhadravati Shikshan Sanstha Bhadravati. Distinguished participants, researchers, professors, scholars, students, and member of organizing committee of this webinar. Friends, the Institute, since its very inception, has made a notable contribution in the area of research. In the month of February 2020, college has organized a national conference and in last month, a international webinar in chemistry. And today, Department of Physics, in collaboration with the Luminous Society of India, organized this international webinar on present scenario of material science. On this occasion, being a head of this institution on behalf of Bhadravati Shiksha Sanstha Bhadravati and Nilkantrao Shinde Science and Arts College Bhadravati welcomes you all in this webinar. And today, I would like to express my most sincere gratitude for your presence in this webinar. I am grateful to Dr. Vivek Sinde sir for accepting our invitation as a inaugurator of this webinar. I am grateful to Dr. Elias Emeka America from Nigeria and Dr. V. Natarajan, ex-scientist of Baba Atomic Research Center, for accepting our invitation as a resource person. Dr. Natarajan have already visited our institution in the month of February 2020 to deliver as a keynote address at the national conference. I am also thankful to Dr. Kokode sir and Dr. Ishwar Mohle sir for accepting our invitation to chair the session. I am grateful to many experts, researchers, scholars who have joined this webinar to share their knowledge. I also welcome many distinguished participants who have joined us. I am grateful to well-known experts from the India and abroad for their participation at short notice. I would like to place on record our deep appreciation of the support and assistance of our Bhadravati Shiksha Sanstha Bhadravati. This webinar will explore several complex interconnected themes. Webinars such as this provide a valuable opportunity for research scientists, scholars, and industry specialists to share experience on record our deep appreciation and rewarding exchange in the next few days. Again, welcoming you all to this seminar. I wish a very success to this webinar and I look forward to learning about the outcome. Thank you and Jai Hind. Thank you.
Thank you, sir. Thank you very much, sir. So you gave the very valuable speech. Now we have to just start the technical session. Before starting this session, I invite Dr. Gajendra Bedre for the introduction of the chairman of this session. Dr. Bedre.
Thank you and Jai Hind.
Good morning. Chairperson of this session, Honorable Dr. Mohodlekar, Dr. Ishwar S. Mohodlekar, working as a registrar, Gondwana University, Gadchiroli. Dr. Mohodlekar has 25 years of experience in teaching to undergraduate students and 2 years to postgraduate. Good morning. More than 6 years of experience in industry administration, work on various authorities and bodies in English, role in institutional Marathi Gadchiroli. He has 25 years of and research activity. 4 students are working, have completed PhD and activity on research. For NSS district coordinator, certificate of appreciation in 2020 by National New Delhi. Here is Challenge Research Academy National Award, India 2020. He also got Maharashtra four students have celebration award in Maharashtra state as a district. New Delhi. Here is Challenge Research Academy National Award, India 2020. He also got
Sir, Moru sir. Unmute.
Dr. Mohli, sir, please unmute your
हाँ सर. Sir, Moru sir. Unmute.
Dr. Mohli, sir, please unmute your
हाँ सर. त्याचा आवाज आहे दादा.
सर कनेक्ट झाले आहेत का?
हाँ सर. सर मोरले सर प्लीज जॉइन. मोरले सर प्लीज जॉइन. सर मोरले सर प्लीज जॉइन. मोरले सर प्लीज जॉइन.
हो सर तुम्ही बोला ना सर. तुम्ही अनम्यूट करा सर. अनम्यूट केलं की आवाज अनम्यूट आहे.
मोरले सर प्लीज जॉइन.
तुम्ही डिस्कस करा सर. तुम्ही बोला ना सर. तुम्ही अनम्यूट करा सर. अनम्यूट केलं की आवाज हो. तुम्ही डिस्कस करा सर.
Hello, Dr. Mohli, sir, please start the speech. Hello, Dr. Mohli, sir, please start the speech.
हॅलो मोरले सर. तुम्हाला आवाज येत आहे का सर? मोरले सर. हा बोला ना सर. तुम्ही बोला ना. तुमचा आवाज येत आहे. हॅलो मोरले सर. तुम्हाला आवाज येत आहे का सर? मोरले सर. हा बोला ना सर. तुम्ही बोला ना. तुमचा आवाज येत आहे. बोलत आहे ना ते.
मोरले सर
बोलत आहे ना ते.
मोरले सर
बोलत आहे ना ते. Mute आहे ना, unmute आहे, दिसतंय ना ते? Unmute आहे ना? बोलत आहे ना ते. Mute आहे ना, unmute आहे, दिसतंय ना ते? Unmute आहे ना? बोलत आहे ना ते. Mute आहे ना, unmute आहे, दिसतंय ना ते? Unmute आहे ना? Mute आहे ना, unmute आहे, दिसतंय ना ते?
हाँ सर मोरले सर Accepted clear. हाँ सर मोरले सर मोरले is trying to connect here. Accepted clear.
रेगावकर सर
जी
सर बोललेत पण ते आपल्याला आवाज नाही आला म्हणून यांचं सुरू करू नका.
मोरले is trying to connect here. काय करा सर Accepted clear.
मोरले सर बोललेत ते पण आपल्याला आवाज नाही आला.
हाँ हाँ
यांचं
हाँ
सुरू करून टाका. सर बोललेत
सर बरं तसं करूया.
नाही आला.
There is some connectivity sir problem arise here. Doctor is Morlekar is not connected here properly. Not audible here. So better way. You have to
मोरले सर बोललेत ते पण आपल्याला आवाज नाही आला. यांचं सुरू करून टाका. सर बोललेत
sir बरं तसं करूया. There is some connectivity sir problem arise here. Doctor is Morlekar is not connected here properly. Not audible here. So
Hello.
better way.
मोरले सर
हा सर. हा बोलले सर.
दुसरं
यू आर नॉट ऑडिबल.
हॅलो डॉक्टर मोर्ले सर.
प्रेझेंट आहे. झालं का सर जॉईन झालं
नो
Dr. Ilyas Ilemke sir. He has completed his PhD from University of Benin in November 2012. He had completed his MSc from Awaka University.
National Research Foundation in South Africa development. Then he got Northwest University postdoctoral fellowship in 2007.
Hello, Dr. Elias. Hello.
Yes.
Yeah,
Can you
you can
hear me?
proceed. Yeah, I can hear you, and you can proceed. Go ahead.
Okay.
Yeah.
Okay. Good morning, everyone.
Good
Yes,
morning.
my name is Dr. Elias Elemike Emeka. The topic of my presentation this morning will be on, though old but new, the case of carbon nanodots. Yes, it is a little bit challenging. I can see there is a lot of network challenges here and there. Sometimes I'm not hearing, but I believe everyone can hear me.
Yes, we can hear
Yes.
you. Go ahead. Please go ahead. We can hear you properly. Go ahead.
All right, so the topic is carbon dots. What do we know about carbon dots? These carbon dots are materials that have nanoparticle size that are less than 10 nanometers. And they are obtained from different sources, from renewable resources, and they are also obtained from graphene or single wall carbon nanotubes. Carbon dots were accidentally obtained in 2004, just like graphene. And how was this obtained? During the refining of single wall carbon nanotubes. It was during the refining of the single wall carbon nanotubes that the scientists come to observe that there are materials which have excellent fluorescent properties. And they were inquisitive to know what kind of material is this. And with investigation, the material was observed to be carbon dots. So these carbon dots are extremely interesting materials which have excellent fluorescent properties. And initially they were obtained from single wall carbon nanotubes, but in recent time, they have been obtained from different carbon sources, from vegetable materials. Any material you can think of that has carbon can give you carbon nanodots, ranging from starch materials, maybe your potatoes that you eat, cassava, your vegetable sources, oils. You can get carbon nanodots from such materials. The process of getting carbon nanodots from graphene can be called the top-down process, whereas the process of getting the carbon dots from polymeric materials or organic materials are regarded to as the bottom-up approach. So these are the two main approaches through which you can get carbon nanodots. So I'll be sharing some of my pictures here. Okay, but before I do that, these materials, they have excellent properties, especially the fluorescent properties that they come to exhibit, because this property has made them to be used, especially in nanomedicine. Thinking about bioimaging, when these materials are injected into living organisms and light is irradiated to the organisms, you'll find out that they are going to glow, showing different colors. And these are what makes these carbon dots to be interesting to the material scientists. So we'll be talking about how are these carbon dots. When you have carbon nanodots, is either you call them carbon dots, carbon nanodots, or carbon quantum dots. Any of the names goes for the material. You will find out that the carbon dots, they have a spherical core, and they have a surface surrounded by different functional groups. All right, this spherical core have a surface, is spherical in nature, and it is basically made of the graphene. you see a graphene framework in the core, and in the surface, you have some functional group ranging from the carboxylic acid functional group, the OH functional group, the amine, the sulfur containing groups. And what does this functional group impact on those carbon nanodots? Remember, when you have things like carboxylic acid, OH, it shows that they are water loving. If we look at the other carbon nanomaterials, like the carbon nanotubes, you find out that most of them, they are not biocompatible. Most of them are not water loving, they are not hydrophilic. But the good thing about the carbon dots is that these carbon dots are hydrophilic. They are biocompatible, they are of low toxicity, and the synthetic nature is very easy and simple. So that has made them to be a very interesting material that is applicable to any walks of life. Talk of nanomedicine, talk of electronics, talk of in different aspects in imaging, in sensing. You can apply all those carbon dots. Because of that, their biocompatibility, because they are water loving, easily dissolve in water, unlike other carbon nanomaterials. And what has made this water dispersible property to be very effective is because of the surface nature of the carbon nanodots. Because in their surface nature, they have some function mentioned earlier, just like the carboxylic acid group, the OH group, the sulfur B. And there's one beautiful thing about them. You can, when you tune the surface, or rather when there is a variation in the surface, during the synthesis, you can actually vary the surface of the carbon nanodots. Variation in the sense that your reaction parameters talk about your temperature, your reaction time, the solvent in which you dissolve the materials, and every other thing, every other reaction conditions will enable the material to have different characteristics. Take, for instance, I am synthesizing a carbon nanodot from a citric acid, which is my carbon source, in the presence of urea. You'll find out, and I'm going to use a hydrothermal treatment at a temperature of about 200 degrees C for like 4 hours. You're going to find out that I might have a carbon nanodot of about 5 nanometers. But when I change the reaction condition, take for instance, I'm performing my reaction at a temperature of 250 degrees C. On that 5 or 6 hours, you're going to find out that I'm going to have a different size carbon nanodots. The size might reduce or the size might increase. So when you vary the reaction conditions, there is possibility that the surface effects will be varied. Okay, so all these reaction conditions affects the surface property.
Hello, doctor.
Yes.
Hello.
Yes. Can you hear me? Can you hear me?
Do you have a PPT? Can you share that PPT with the participant? PPT, PowerPoint presentation?
Yes, I have it. Let me.
Yeah, please share it. Please share it.
Share. Yes, I'm trying to share.
Yeah, please go ahead. Sorry to interrupt you.
It shows I'm disabled to share, so you can enable me from that side.
Oh, okay.
It's showing that I am disabled. So, yes.
It will disable. One minute.
Okay. Yes, I think I can see it now. Sure. Try.
Yeah, now we can see. Alan? Yes, we can see your screen now.
Yes, I'm trying to share it. I am trying to share it. I'm having some challenges here. Okay. Can you see it now?
Yeah. Please go ahead.
Okay.
We can see your screen now. Yes.
You can see my screen. Okay. All right. So,
Thank you.
all right. So before I was interrupted, I was talking about the carbon nanodots. Yes, I have said that these are materials, or rather nanoparticles, which have particle size less than 10 nanometers. It was accidentally discovered in 2004 during purification of single wall carbon nanotubes. Okay? They are new class of fluorescent material. In fact, what makes carbon nanodots to be spectacular is because of their fluorescing properties. They could serve as alternatives to semiconductor quantum dots. When we talk of semiconductors, typical examples are the zinc oxide, the titanium oxide, cadmium selenide, and a host of them all. This new set of nanomaterials, which are the carbon dots, could serve as alternative to these semiconductors and organic dyes. Because of their luminescence properties, they are used, especially in nanomedicine, for bioimaging. And they can show different colors because of the variation in energy gap, or rather band gap. They have zero-dimensional graphitic structure. I was explaining before that the structure of carbon nanodots is in such a way that it has two parts. It has a spherical core and the surface. And the surface is made up of some functional groups, such as the polyaromatic functional groups, like containing the carboxylic acid, the hydroxyl group, and some other heteroatoms. And these surface functions, or rather their surface chemistry, can be varied, by introducing a whole lot of functional groups, by doping as well. You can vary the surface effects. And when you vary the surface effects, there is going to be variation in their sizes. And when you vary their sizes, automatically their luminescent properties changes. Okay, so all this will enable you to be able to get different carbon nanodots of different photoluminescent properties and from different sources as well. One good thing about the carbon nanoducts are they can easily be synthesized. They are also of low toxicity and they are eco-friendly. You can even have large-scale production of the carbon nanoducts from simple sources, from agricultural waste, and also they are of low cost as well. So that is one of the greatest benefits of the carbon nanoducts over the other carbon nanomaterials. When we are talking of carbon nanomaterials, remember, we talk about the carbon nanotubes, which many people knew. We talk about the graphene. We also talk about the single wall carbon nanotubes and the rest of them. But the carbon dots, or rather the carbon quantum dots, is one of the recent materials that is gaining interest among the researchers because of its low toxicity, biocompatibility, and water dispersibility. In fact, that is a very interesting property of this carbon nanoducts because it has the ability to dissolve in water. And because of that, it is applied in a whole lot of things. Carbon ducts have excellent photo absorption capacity with electron accepting and transport properties. When you have carbon dots, remember their size are very small, and that's why they are called quantum dots. Their size is below 10 nanometers, and because of that, they will be able to absorb energy from the radiation, from the electromagnetic radiation. They can absorb energy, and when they absorb the energy, they are excited. Electron moves from the valence band to the conduction band, and when that happens, there is an energy band gap, and the size of the material determines the size, or rather the size of the energy gap, or rather the energy gap rather. So if the material is lower, you are going to have a larger band gap, and in that case, the material is moving towards a blue shift when the size is lower. But when the size increases, is having a red shift. And when I say red shift, it's moving from a lower wavelength to a higher wavelength. And in that case, you are going to have a color variation. Okay? And these properties have enabled them the opportunity as materials to be used in energy conversion and energy storage. When we are talking about energy conversion and energy storage, we will remember the lithium ion batteries, we will remember the supercapacitors, and a whole lot of them. They are used for energy storage and or energy conversion. So carbon dots, because of all these properties of carbon dots, they have been applied a whole lot of things in optoelectronics. Remember, in optoelectronics converting from a higher wavelength to a lower wavelength. And you can also have down conversion, especially for the solar cells, whereby there is a movement from a lower wavelength to a higher wavelength. So all those carbon nanodots can enable the application of such materials for down conversion solar cells and also for up conversion, especially in optoelectronic materials. All right. There are trends in the morphology, or rather formation of carbon nanodots. As I earlier told you, in 2004, it was isolated from purification of single wall carbon nanodots. But as the year advances, you find out that the scientists begin to discover that this is a material that has a spherical core, which is of graphene framework, and it is surrounded by surfaces. We can modify these surfaces by introducing some functional groups. And you look at it, in 2006, there is some modification of the surfaces, and the modification of these surfaces enabled them better application, or rather better properties or enhanced properties for different other applications. So moving from 2006 up until 2010 till the present date, you can see that there has been advancement in different structures and different topologies of the carbon nanodots. I hope we all can see it.
What location decided to visit the mission?
Okay. So earlier I mentioned about the sources of these carbon nanotubes. Carbon nanotubes initially was discovered from the single wall purification of the single wall carbon nanotubes, or rather carbon nanotubes. And the second source is from biomass or from renewable resources, such as the fruits you eat, the vegetables, the flowers, starch containing anything that has carbon can give you the carbon dots. Okay? So for the carbon nanotubes, I earlier told us that it is a top-down approach that was used to get carbon dots from carbon nanotubes. But for the case of the biomass, you use a bottom-up approach to get the carbon dots from these renewable resources. However, the carbon dots from different sources can give us different fluorescence property. So when you have a carbon dot from fruits, you find out that the carbon dot from fruits can give you different fluorescence property from the carbon dots from the single wall carbon nanotubes. So from different sources, and that is the beauty of the materials, that I can decide to get my carbon dots from potato. When I get it from potato, you find out that the fluorescent properties that I'm going to have from the carbon dots from potato is going to be different from the fluorescent properties that I'm going to get from carbon dots from flowers or from vegetables or from oils as well. So all this variation in properties is a very interesting thing when it comes to material science. And that's why in 2020 and beyond, it is the interest of the scientists to continuously look for the better properties, or rather for the greater properties of these carbon dots. I also said that the most interesting thing about carbon dots is their valuable photoluminescent properties. They possess great fluorescent properties, better than traditional fluorescent dyes. We've been using dyes, for fluorescence, but I'm trying to tell you at this moment that carbon dots have interesting, or rather greater fluorescent properties than the traditional fluorescent dyes that we know. And they are photostable, they resist photo bleaching and non-blinking. And other properties that I earlier said is their low toxicity, they are very chemically stable. You can functionalize them easily. What do I mean by functionalization? When you're trying to change their surface effect, or rather the surface functional groups, you're trying to functionalize the carbon nanodots. And because of that, they give you various properties. And that is the beautiful thing about material scientists, trying to pick up any material, just functionalize the material, and you are going to get a property of your desire. So, and this is what is making material science a very interesting area in the present science and technology. So I know this conference is organized by physicists, and I know one interesting thing about the physicists, they like to hear things about quantum yield. So you will be calculating, because first of all, when you synthesize the material, you're going to do a whole lot of characterization. And one of the characterization, which is peculiar to the quantum dots, is that you're going to do the photoluminescent property. And when you do the photoluminescent property, a typical example of a photoluminescent absorption is what is showing on the screen. And when you look at it, you find out that it has the intensity. You excite the material at a particular wavelength, and it's going to emit at the other wavelength. So when you look at some of the material, once you excite it, maybe at a wavelength of like 360, 365, you're going to see emission. And you're going to calculate the quantum yield. This quantum yield will be able to help you know whether this material is highly the energy gap, and how is it going to be used in things like energy storage. And with the idea of having the quantum, you will be able to predict that So when you have a material, there's a formula that is showing on the screen through which you can calculate the quantum yield of a material. Okay, there will be a reference material, and the reference material is denoted by XT, and the reference material you could use is a quinine sulfate. So when you excite the material in your photoluminescent machine, you're going to get your spectra. And when you get your spectra, get the intensity of the spectra. I in the equation is represented as the intensity, A is represented as the absorbance, and the N is represented as the refractive index of the solvent into which the material was dissolved in. So get all these values, input it into the equation that you're seeing on the screen. You're going to get the quantum yield of that material. So the higher the quantum yield, definitely you are going to see that the material will be of high excellent, or rather excellent fluorescent property. Okay, so pardon me, because I have a chemistry background, I'll be talking much about chemistry. I hope the physicists, you will bear with me. But physics and chemists, they are friends. So I believe most of us, the participants, will be understanding some of the chemical terms that I will be using here. So I earlier said about the synthesis. We have two major syntheses, the top-down and the bottom-up approach. When you look at the screen, you are going to see that the top-down is from a bulk carbon material, which I earlier said, your graphite, your carbon nanotubes. You just use methods like oxidation. When you have graphite, you just do chemical oxidation, and chemical oxidation of the graphite will give you the carbon nanotubes. You can do the synthesis through electrochemical methods or by laser ablation. Then using the bottom-up approach from your organic materials or your polymeric materials or your fruits, your vegetables, your starch source or other carbon sources, it is a bottom-up approach because it is believed that it's from a smaller molecules to smaller molecule as well. For bottom, from the nomenclature bottom, you already understand what it means. So through these two principal methods, you can get your carbon nanodots from two principal sources, which are diverse on their own, especially in the organic molecules. There are a whole lot of organic molecules. It could be by biomimetic. Biomimetic in the sense that already existing chemicals, but those chemicals are of biological interest. Think of the citric acid. They are chemicals, quite all right, organic chemicals, but they are friendly organic chemicals. So you can get it from your agricultural waste, like your fruits and other things. You can also get it from those chemicals like the citric acid, in as much as it has a carbon source. Okay, yes, you can get it from there. So a typical example of the picture by the right hand side is carbon dust made from an easy chemical oxidation using an arc synthesized carbon byproducts. You could see from the right hand side, the single wall nanotubes, which was purified. So the byproducts of that single wall nanotube, from there, you do ultrasonic dispersion. That ultrasonic dispersion is going to give you your carbon dots. And when you centrifuge it, you can see the process, you get your nano carbon dots. Then you can see another one, potato, getting your carbon dots from potato. It looks wild how carbon dots can be obtained from potato and from some other carbon source. Let me tell you, material science has gone haywire in the sense that any material that is around you that has carbon source can give you carbon nanodots. Look at the picture there from the potato. You find out when you mash your potato, it has starch content, and then the components of the starch more or less are carbon. So hydrothermal synthesis at a temperature of 180 degrees C for 18 hours will be able to give you carbon dots. So you have to perform this reaction for 18 hours. So what is happening while the reaction is going on? the materials are being disintegrated, and when it is being disintegrated, it gives you another mass. So you can see the reaction time and you can see the reaction temperature. Okay, so you may not be able to just get a material now that is a carbon salt material. You just heat it for like 10 at a temperature of 50 degrees C, maybe for 2 hours. You expect it. That is why conditions in reactions are very, very necessary. You must follow those conditions, and that's why earlier on sometimes you stumble into some materials that you never expected because you have allowed the materials to undergo some conditions which you never expected. And before you know it, when you test the materials, you find out that the materials have properties that you never expected it to happen. And that is one good thing about material. You could be synthesizing another thing and you are going to get another thing. And whatever thing you might get might be of immense use to the material science. By the right-hand side is another synthetic method in which carbon dots was obtained from egg yolk oil. We all eat egg, and when you eat egg, you know how the yolk looks like. From the structure, you can see it's yellowish in nature. It undergoes a microwave irradiation. You can see the microwave there. You heat it for a very long time, and you extract the oil from there. Once you extract the oil, dialysis of the oil will give you the carbon dots, and you centrifuge. That is what you're seeing in that tube. So all these materials are very easy to make, and that is the good thing about carbon nanodots in present times. So another synthetic method you can see there is, hello, I hope you all are hearing me. Hello?
Yes, we can hear you. Please go ahead. Please go ahead.
I want to be sure. Yes.
Yeah.
But I know I'm not talking to the spirits. Okay. Thank you. So this is another synthetic procedure from citric acid. When you look at the structure of the citric acid, it has carbon sources, a citric acid and glycerin, heating it at a temperature of 120 degrees C. When we look at the old one, it was heated at a temperature of 180 degrees C. So the energy band gap is decreasing. So you see the link in this material. So if I need an energy gap, a lower energy band gap, what it simply means that I have to modify the surface of my carbon nanodots so that I will be able to get a lower energy band gap. But if I need a higher energy band gap, what does it mean? I need to reduce the surface, the functional groups on the surface. So all these things determines the kind of carbon nanodot that I'm going to have. Okay? So in the other side, we'll see a typical example of a multicolor emitting carbon nanodot using citric acid, urea, and 3 different solvents. When I do my synthesis in different solvents, you find out that I'm going to have a particular color being emitted. When you look at the reaction, urea and citric acid in the presence of water under solvothermal. Okay, we are using solvothermal in this case. When it is water, when the condition is underwater, it is hydrothermal. But when it is other solvent, like you can see in the case whereby dimethyl formaldehyde is used and glycerol, you call such conditions solvothermal. But the first one that is underwater is a hydrothermal process. So in that case now, you see the nature of the carbon dot that I have and the fluorescent properties emitting blue colors. When it is under a glycerol solvent, I'm getting a green color, and you can see the surface groups are changing or rather increasing. Under dimethyl formaldehyde, I'm getting a reddish or a pinkish color, which shows that the nature of the solvent too will affect these materials as well. So I can play around with my materials to get whatever fluorescent properties that I want. That is just the message that I'm trying to pass across. You can, tune or rather change the surface effects of your carbon nanodots to be able to get a particular property that you want. And that is the beauty of the material synthesis. All right. So this is another example of whereby a carbon dot are doped. Okay. In the first scenario, it's still urea and citric acid under hydrothermal synthesis, giving us that carbon dot. Okay. Then in the second scenario, you see an element is introduced, which is zinc. So I could decide to modify the properties by introducing a metal ion into the carbon nanodots. Okay? And in that case, I'm going to have a composite. So you can actually have a composite of carbon nanodots in order to extend the properties, or rather to enhance the property for any application that you want. It all depends on what you have. Then you have to look at the properties of those individual material that you have compounded. Take, for instance, I'm looking at the photocatalytic reaction, and I know that zinc oxide is a very good catalyst. So what do I do in my carbon dot? I want to extend the property, or I want to enhance the property of that carbon dot. I could include or inculcate into that carbon dot the zinc oxide. And in that case, I'm going to have a what? A composite. And that composite might give me an activity which is higher than when I am using only single carbon nanodots. So these are the ways through which we can just change our materials to be able to get a desired property. So you could see the excitation of the electrons moving from the highest occupied molecular orbital to the lowest unoccupied, and when things like that happen, there is creation of holes and creation of holes, recombination, and a whole lot of things. So you can control all this by, tuning your material or by modifying the surface effect of your materials. Okay, so we'll talk about of this effect of the surface oxidation. Surface oxidation, surface modification. Yeah, I have been explaining that. So in this case, there is treatment of citric acid under microwave irradiation condition at a temperature of 160 degrees C. Okay, remember in the earlier one, we talked about a reaction of a citric acid with urea, in different solvents. But in this case, we can see that urea is not added in this case. But the source of the carbon is citric acid. But it's a different reaction condition with microwave irradiation. At a temperature of 160 degrees, under 1 hour, this reaction looks other reaction takes up to 18 hours as the case may be. In this case, so what am I trying to say? Different reaction conditions to affect the material property. Microwave irradiation method is one of the fastest methods of in recent times. It can perform your reaction under 10 minutes if you want. You can see this kind of material that we use. Instead of using urea, we are using formaldehyde. It is under formaldehyde, and it is temperature of 160 degrees C under 1 hour. And we are able to get all these materials, carbon nanodots, with different surface functions. So we could decide to use a different mechanism, or rather different reaction mechanism. In this case, microwave is used. In the other case, we use subthermal or hydrothermal. Some other person could decide to use electrochemical method. The beauty of it is that you're going to get carbon nanodots of different sizes and different variation in their work, in their properties. So the effect of the surface oxidation, rather, is the higher the degree of the surface oxidation, the more surface defects and emission size, resulting in redshift of the emission wavelength. I've said that earlier, that when you have more surface functional groups, okay, there is going to be a shift to the, there is going to be a redshift. And redshift simply means increase in your wavelength. Maybe you're moving from 300 nanometer to 400 to 5. That is redshift, okay? And that symbolizes that the particle size is increasing, and that is a decrease in your energy bandgap. Okay, so those are the effects of the surface oxidation on the carbon dots. We have all just said this about the properties of the carbon dots, their preparation, different preparation. I would just be happy to see or to hear that already after this conference that people will be preparing different nanodots, carbon nanodots from different sources, and they're getting different materials. Now let's go into the application. We have mentioned some of them earlier on, but let me have a recap that the applications of this carbon nanodot is widely applied. You can see from the diagram there, the core could have in bioimaging because of that their fluorescent properties. So if you want to diagnose maybe a particular disease, maybe a tumor cell, you just inject it into the organism and pass irradiate where you have the tumor growth, that the carbon nanodot will glow, showing you different colors. And with time, it's going to show you how the growth is being removed, or how the growth, it is being distributed in that growth in order to remove the growth from the organism. So you use it in bioimaging, use it in light emitting diodes, in mass spectrometer. You also use it in a catalysis. It could be electrocatalysis, it could be photocatalysis, organocatalysis, in drug delivery, in gene regulation, and a whole lot of other things. Okay? So they can serve as nanoproofs for the fluorescent-based detection of environmentally relevant powdery metal ion. So you can actually use it as an environmental proof. Say, for instance, through an electrochemical wave, you just have your electrode, and you mark your electrode with the carbon dot. You find out that it could help you detect the quantity, or rather the concentration of a heavy metal at a particular thing. So you just want to determine the concentration of this heavy metal. You can use all the carbon dots as nanoproofs. That will help you. The more you have the heavy metals, you will see the glow. You will see from the way it glows, it will show you that you're having higher concentration. When the quantity is reduced, the emission is going to reduce as well. So these are just the applications, and it's making the study of this carbon nanodots fascinating in present times. They can also be applied in optoelectronic devices due to their strong excitation independent photoluminescence emission and strong up-conversion fluorescence. Okay? Photoluminescent property is one of the best properties that this carbon, and scientists are taking advantage of that a lot in up-conversion optoelectronic materials, because the wavelength is going to move from a higher wavelength to a lower. Wavelength when you talk about activities. How do you do that? You could see a typical Staphylococcus aureus. When the carbon nanodots are introduced in having this bacteria, you see the way it marks the bacteria and renders the bacteria useless. So in that case, you can see that they have great antibacterial or antimicrobial properties. You can use them also in photocatalytic activity. Okay, look at that diagram there, whereby carbon nanodots is synthesized from citric acid, and in the presence of glycerol, the cow urine acts as a reducing agent, or a kind of. Remember, in the other case we use urea. In this case, they are using a cow urine, which is a waste. Okay, it's just like turning waste to a resource. So when you have your cow urine, just add your cow urine to your citric acid and your glycerol and heat it at a temperature of like 150 degrees C. Under reaction time of 4 hours, you're going to get your nanodots. Okay? And in that nanodots, you could functionalize it by introducing.
Hello, sorry to interrupt you. Yeah, I can hear you, but there is a 10 minutes left to go for your presentation. It's a time constraint, so
the what?
Please. 10 minutes. 10 minutes
Okay,
only.
time. Okay. I'm running up. I only have one slide left. Okay.
Yeah. Thank you. Thank
Yes.
you.
Okay. Thank you. So you see the photocatalytic activity. Titanium oxide and zinc oxide have very high photocatalytic activity. But when when you compound carbon dots with such materials, you find out that it's going to have enhanced photocatalytic property. And that photocatalysis is just about the sensitization, photosensitization. When you irradiate them with the light energy, you find out that is excitation of electron or other movement of electron from the valence band to the conduction band, thereby creating an energy gap. So the energy gap now will determine their activity, the photocatalytic activity. So with carbon dots compounded with titanium oxide, you are going to see a marvelous photocatalytic activity. In drug delivery, I've mentioned earlier, it serves both for therapy and for diagnostics. Okay, when you can see that a typical example of the rat, whereby carbon nanodots are used as carrier and oxaplatin. Oxaplatin is an anti-cancer agent, but the carbon nanodots are used as carrier. You see the way they carry the drug into the where you have the tumor cell in the body of the rat, and gradually the glow diminishes. That means that gradually the cancer tumor disappeared. So they are wonderful materials, and they have so many other applications. Because of time constraints, we could not continue. But I believe with this, in the next, when the lockdown is over and when the scientists go back to their lab, they should try to start getting different carbon dust from different sources. This material is a very wonderful material, and believe you me, in material science, one would digress from having carbon dots, inculcating so many other materials into the carbon dots. We will be able to play around with our materials and to get excellent materials for different applications. Thank you. Thank you very much.
Thank you, doctor. There are few questions arriving from the participants. I would like to ask some question on behalf of the participant. I'll take only one or two questions. So Dr. Achole is asking, carbon nanotubes or carbon dots be used for protection of COVID-19? Is there any use of this material?
Yes. Okay. Can I answer the question now?
Yeah, sure. Go ahead. That's what I'm asking.
Okay. One thing in material science is that we continue to try. And COVID-19 is like a stranger to us. And scientists are trying. Scientists are not sleeping because we need to get a solution to this COVID-19. There is no, I may not tell you that it will cure it. I may not tell you that it will not cure it. But with scientists, one thing, we can get our carbon nanomaterials. It has been used in cancer treatment. There is possibility that carbon nanodots, when you inculcate other materials into it, is going to go a long way in the cure of this COVID-19. So it is not ruled out in trying to use carbon nanodots because they are of low toxicity and they are water dispersible. That is just one good, or rather the property that it has that might make it to be used for the treatment of the strange disease in our environment recently.
Yeah, okay. I hope Dr. Achole is satisfied with your answer. Another question is from Nigeria, Osofile Omodese. He want to ask you what kind of element or material can be used for the functionalization?
Okay. She is asking what kind of materials can be used for functionalization. You can use a nitrogen source. You can decide to dope with nitrogen. And there are materials that you can use that can give you nitrogen. Take, for instance, phenyldiamine. Diamine materials can be a source of nitrogen. So in that case, you have succeeded in doping the carbon nanodots with nitrogen. Okay? There are dicarboxylic acids. So we can decide to change the the number of carboxylic acid functional group in the surface, I could decide to get another. There are a whole lot of dicarboxylic acid. I could decide to use a particular one, and maybe oxalic acid. I could decide to use another one. In that case, I am changing the functional properties, or rather the functionalization of the surfaces.
Okay. I hope the last question is like, how can surface oxidation be prevented in carbon dots?
Prevention of surface oxidation, it is a challenge. It is a challenge because remember earlier I said that we have a core, a spherical core, which has graphene or rather graphite framework, and the surface that you can functionalize. Those are the two major parts of that carbon dot. So preventing oxidation on the surface is only when you don't have oxygen functional groups there. That is the only time you can. But it has been a challenge preventing oxidation. You can't do without it for now, as much as I know, because of that property of the carbon dots having two parts of the core and the surface, and that surface is made up of some functional groups. So you cannot rule out, in as much as in organic chemistry, those materials can be oxidized. There is no way you can stop it for now. But I know with time, when research goes on, there could be solutions.
Yeah, okay. Thank you. I hope all the participants are get satisfied with their answers. So I would like to thank you, Dr. Elias, for having wonderful, intellectual, and informative lectures on this one-day webinar on present scenario of material sciences. So thank you very much. I hand over to the Dr. Dagavkar sir, who is the convener of this webinar. Thank you very much. Thank you, Dr. Elias. Thank you very much.
Thank you.
Thank you very much, sir, for your very informative lectures and a very nice presentation. Also, the very satisfactory answer to all the questions of the participants. Now we are going to start the second session. Now again, I request Dr. Garendra Bedre sir for the introducing the chairman of the second session, Dr. Enes Kokode sir.
Good afternoon. Chairperson of this session is Dr. Honorable Dr. Enes Kokode sir, Principal NH College, Brahmapuri. Dr. Kokode sir has 35 years of teaching experience. He has 16 years of experience as a principal. He is the director of BCUD, Gondwana University, Gadchiroli. He worked as a Dean Faculty of Science, Gondwana University, Gadchiroli. He has published 150 research papers. 5 students awarded PhD under his guidance. 3 students have submitted their thesis. He got Best Principal Award of Nagpur and Gadchiroli University. He worked on all university bodies. I request Honorable Dr. Kokode sir to conduct this session as a chairperson. Thank you.
Thank you very much. Am I audible?
Yes, sir. Please go ahead.
Okay. Thank you very much. Thank you very much. My tributes and best wishes to the President of the Education Society, Mrs. Honorable Secretary, ex-MLA Nilkant Raoji Shinde sir, the Joint Secretary, Dr. Vivek Shinde, my friend, Dr. Karthik Shinde, Vishal Shinde, Honorable Principal of the College, Dr. Ladke sir, Vice Principal Harne sir, the convener of this program, Dr. Dahegavkar, Dr. Gajendra Bedre, my student, all the participants. And I have to introduce Dr. Natarajan Venkat Raman, the honorable guest present here. And just now we have had a very good talk of Dr. from South Africa and delivered a very nice talk to all the dignitaries, all the principals, professors, associate professor, assistant professor, scientists, and the delegates for this international webinar. First of all, I heartily welcome the honorable guest, distinguished guest rather I will say, and very well renowned scientist, Dr. Natarajan Venkatraman. On behalf of the organizing committee and being the chairman of this session, I heartily welcome Dr. Natarajan Venkatraman. He is a senior professor and his discipline of research and scientific work is chemical science. This is a broad discipline, chemical science, and having the division radiochemistry. He worked in Bhabha Atomic Research Center, Mumbai, and he done his all research work in a very applied fields. For example, he work in solid state chemistry area where he has concentrated his research was mainly on photoluminescence, the TSL, and electroparamagnetic resonance EPR. The radiation effects he has studied in the very deep sense, analytical emission spectroscopy. He is having the very keen interest in this analytical emission spectroscopy and very applied and very powerful research he has carried out regarding the recovery and purification of plutonium. In Bhabha Atomic Research Center, Dr. Natarajan has carried out the recovery and purification of the plutonium. He has a number of publications in the applied fields, having many colleagues and scientists working under him, to whom he has given a very good guidance. And his all the that is the research work he has done is very applied and very powerful. Some I will tell you some example. The photoluminescence of Fe3 plus, the photoluminescence investigation of the near white light emitting perovskite ceramic, the ESR dosimetry using inorganic materials instead of Li2CO3, radiation stability of the uranium 5 plus, absolute fusion yield measurements. The fusion yield measurements he has done. The preparation and characterization of tunable phosphors. Preparation and characterization of tunable phosphors. Synthesis and photoluminescence investigations of white light emitting phosphors. This is a very applied type of the research while making the white LEDs, the solid state lighting area, and photoluminescence investigations of white light emitting phosphors. He has also done the research work like alpha irradiation effects on the superconductors, very applied field. The alpha radiation effects on the superconductivity of the most of the materials. Also, he has done the work in electron paramagnetic resonance (EPR) of the AM241. So very much applied research was having so many contributions in the scientific and the applied type of the investigations. And he is a very eminent scientist we are having with us. I heartily welcome on behalf of the organization committee, Dr. Natarajan Venkatraman sir. You are heartily welcome for this session, and I request you to deliver your lecture. Thank you, sir.
Am I audible now?
Yes.
Am I audible to everybody?
Yes, sir. Please go ahead. Please go ahead.
First of all, I want to thank the management of Nilkant Rao Shinde College Arts for giving me an opportunity to talk to this August audience. And my special thanks are due to Professor Ladke for giving a very elaborative introduction to me. And the purpose of my talk today is to explain the electroluminescence, luminescent devices from the start till 2020. What are the initially how it started and how it is going now? This I will be describing in about 45 to 55 minutes. I request you to kindly bear with me. I want to complete the thing and I will try to explain the best of my capacity. Slides, please. I will be sharing slides. Just a minute. This one. Is it visible to everybody? Are you able to?
Yes, sir. Yes, sir. Yes, sir.
Go ahead
Please,
now.
please go ahead.
First, I want to thank Professor Elias Elimike for introducing carbon dots in an excellent way. In my talk, it is 1 or 2 slides. Carbon dot application. I will just mention briefly. Okay, this talk will, as I mentioned, it will cover electroluminescence from basic to advanced. Okay, what is electroluminescence? It is basically luminescence. Everybody knows it is the emission of light. Electroluminescence means when you excite a material with electrical energy, either current or voltage, light is emitted. This is electroluminescence. It is a non-thermal, no heat is involved. Non-thermal generation of light. These are the some typical displays in the 1960s, 60, 65. You can see they are all very lightweight displays. You can see these are all packet displays, 1960 to 70. Can I go ahead? Can I go ahead? And this is a laptop monitor in 1983. Those days, data analysis used to be done using laptops. So that time, this display is a real display. Okay, I will explain this later. This is a lightweight. Size is for watch and watch dials and packet lighting. Military used to have lighting EL device. They will carry. And, okay, I will explain later. Now we go to next. As I mentioned, electroluminescence is emission of light by a material when it is subjected to electric field. You have two types of electroluminescence. You can classify into two. One is injection electroluminescence. Another is high field electroluminescence. Injection electroluminescence means, as it is mentioned, it is low current, low field operation. A semiconductor is there. You inject electron and current and electron hole recombination takes place at BN junction, and light is emitted. It is simple. It is the principle of LED. You pass a current, the light emitting diode, electron and hole. What is hole? Hole is an electron vacancy. Suppose you take a semiconductor in the valence band is up to valence band, all electrons are filled. Suppose one electron is removed from there by the electrical energy and taken to conduction band. That is the difference. The difference in energy between valence band and conduction band of a semiconductor is called band gap. It is, let us say, it is of the order of 1 or 2 eV. So 2 eV energy is pumped by electrical device, and then you can generate what you call, one electron can be taken to conduction band, and you will, that electron vacancy is called hole. It behaves like a positive charge. So P means hole, N means electron. So PN junction. And when the electron hole recombination under high electric field, when it occurs, and then what happens? You have to have protective electrodes, insulator, and other thing, and then you should have the luminescent center. Then in the material, then this is called charge injection. You inject electron, and then radiative electron hole recombination takes place. So this is you can see the diagram. You see, you will have this is AC device. Your insulator will be there. Device. Then you will have the insulating film. Then you have the material, EL material, whatever it is, zinc sulfide or whatever it is. And then you pass a AC current. Then you have everywhere one activator will be there, which will be the luminescence center. For example, electron injected passes through this material. and then it is having the luminescence center like copper or whatever it is, copper, manganese or anything. Then these electrons, when they are moving, they hit the luminescence center in the material, and then that center gets excited. Copper copper plus or silver plus, whatever it is, it goes to excitation, comes back and gives light. So it is called impact. First one is called simple luminescence. Second one is impact ionization. And impact excitation of the luminescence center, and then light is emitted. And you can have blue color, green color, yellow color, depending on whatever is the material. For example, blue color in the earlier days, zinc sulfide copper was used. For green color light emission, zinc sulfide doped with copper, with aluminum. Here chlorine, and for green, yellow, zinc sulfide, copper, chlorine, and manganese. These are all 1960 to 70 studies. Okay. Then electroluminescent material, there are other materials which also can be used. Zinc sulfide manganese is the most popular EL device. With boron impurity also gives a blue color. It is also, when you pass current, it will give blue color. It is electroluminescence. Then I come to the history, which is, I think students will be happy to listen. The electroluminescence was first reported in silicon carbide. So long back, they were studying single crystal. Electroluminescence single crystal was the first study which was initiated, and later it shifted to powder. Electroluminescence was first observed in silicon carbide by Captain Henry Joseph Brown. It is 1907. And the next report, in between some reports are there. Next slide I will tell you. But this particular slide I had picked up from somewhere. It is going to 1923 slide, where O.V. Losa reported electroluminescent silicon carbide crystal. Again, it is single crystal study. Then you come to thin film structures. These later, in between powder reports are there. First thin film electroluminescent structure, 1950 by Blasenko and Popko reported. Then Saxman and Keschwell conducted research between 64 and 70. And they thin film electroluminescent display with high luminescence was fabricated. And till now, this design is not changed very much. In between 1968, Aaron Wecht demonstrated a direct current DC powered EL panel using powder phosphorus. Okay. Here DC is not popular as on today. I will come to the thing, this detail later. Now AC thin film electroluminescent display is the one which is maximum reported and studied. Okay, now the history further, 1936, Georges Destrap, he discovered EL emission in zinc sulfide copper suspended in castor oil. Zinc sulfide copper was suspended in castor oil and electrode and mica insulator. And when current was passed, you got a yellow emission. Then later, he replaced oil and mica with polymer binder. So means powder form. This led to low light level EL lamps. Then GET Sylvania in US, they fabricated ceramic AC EL lamps. The EL phosphor was coated on stainless steel plate. 1950 to 55, US military used it extensively. It minimum power and long lifetime. This is the characteristic of these lamps. And even in aircrafts, exterior safety lights for aircrafts was these EL lamps were used. Then Vasanko and Popko, I described in the earlier slide, we prepared AC thin film EL from zinc sulfide manganese. Brightness better than powder. AC thin film is giving better power than powder, but lifetime efficiency was poor at that time. And later, Saxman and Keschwell studied the driver voltage for the TFEL with how to get high luminescence output. But their device was not reliable. So then 1965 TFEL dot matrix display was demonstrated in US by Sigvatron company. Then Aaron Wecht mentioned in the earlier slide, he prepared a DC powder phosphor EL panel for watch dial night shift backlight. This is 1968. Then AC thin film high brightness long lifetime was developed. Inoguchi, he is the pioneer of current AC EL devices. Toshio Inoguchi, Sharp Corporation, 1974. He used zinc sulfide manganese as the electroluminescent phosphor and yttrium oxide as insulator. Then monochromatic EL electroluminescent display for grid and data general laptop was produced by Planar Company and Sharp using zinc sulfide manganese, amber color. You see this display. This is the amber color, which was the EL device, which was extensively bought those days, 1983. In 1993, an EL device had a drawback. The blue phosphor was not good. And first time in 1993, strontium sulfide copper was discovered, reported as a blue EL phosphor. And then full color display devices were started making. But AC thin film structure most successful and commercially available even on today. And then Zingwai and Canada, the thick film EL technology. He used that and he prepared, this company, it was called iFire. They prepared a color TV using 2 layers of electroaluminum phosphor, thick electric plus zinc magnesium sulfide doped with manganese for green emission, barium aluminum sulfide doped with europium for blue emission. This could produce all colors. Unfortunately, 2003 LCDs started developing and their cost was so low that EL TVs were very costly. Technology was not very good, so they could not commercialize this particular product. And then 2012, Sungwan hybrid using cadmium, selenium, zinc sulfide, organic quantum dots blended in polymer. He reported a AC electrolysis device. And still commercial, not commercialized it. And then 2020, Samsung is reporting that they are on the job for preparing quantum dot emissive TV. Quantum dot emissive electroluminescent TV. Emissive means electroluminescent TV. Okay, then one more reason why EL research was not taking up was OLED became very popular. OLED is also EL only, but that became popular and it was commercialized very fast and it could compete with LCD technology. So it is developed like anything. Well, there is one side shoot of this electroluminescence, that is blue LED. Blue LED combined with phosphor, that is initially BAM europium 2 plus, barium magnesium aluminate europium 2 plus. This was the technology which is used for the LED lamps, white light emitting LED lamps. Anyhow, it is a different topic because blue LED is EL, but phosphor is photoluminescence. So blue light is absorbed by the phosphor, it gives white light. So this I am not going to discuss in this talk. Then see, there are powder and thin film, 2 ways of getting a EL, and then you have DC and AC. Powder base, earlier days, that is 60, 70 and all, so around 60, 50, 60. Frequently used this powder based purpose, backlights for liquid crystal display. Even up to 2000 it was used. They consume little electric power if it is DC. Convenient for battery operated devices. This powder phosphor, gentle green, cyan, yellow. Okay, these are all old, up to 90, not after 90, 85. They require relatively high voltage. If it is AC device, it requires high voltage, 60 to 600. And thin film phosphor electrolysis device is manufactured medical applications, the rugged and high resolution display, even on silicon substrate. These are all development up to 2000. Then luminescent mechanism different for powder and thin film devices. AC, if you see AC powder, let us say zinc sulfide in a dielectric, it is having copper. Copper is deposited along structural defects in the grain. In strong electric field, copper needles serve as source of electron and holes from the host matrix. And holes are created at a luminescent center. Luminescent center adjacent to interface, means interface, copper into zinc interface, where the electron hole recombination and then copper is dropping and activating the luminescent center. Copper is activated by the hole. And when you reverse the field, same thing happens. Again, recombination luminescence. Basically, holes are at the luminescent center, electron is released from the host, like that. And during high bright operation, what happened? Copper sulfide noodles become excessively hot in a DC operation. And this weakens the noodle structure and injection, eventually luminescence comes down. This is AC. Okay, DC powder is similar, but there is a difference. In DC, copper is outside the grain. Okay, outside of the grain. Copper is separate. It is not in the host grain. Then constant high field is applied to induce migration. This process results in copper noodle directed to grain. The needle structure concentrate the applied field sufficiently to inject electron to phosphor. An electron accelerate in the zinc sulfide conduction band, then they hit with the luminescent centers. By impact, with high velocity they hit, the luminescent center gets excited and then they emit light. Okay. Then continued copper UV fusion eventually destroys the noodles and luminescence ceases. I mean, DC, high brightness operation, DC cannot be used. Here, since the field is reversed, that section is not much. Here, field cannot be reversed. So when you use for high brightness DC lamp, this will lifetime will be very less. And the luminescent thin AC structure, very similar to it, what they say hot electron mechanism. Hot electron means higher energy electron hitting the luminescent center. That's what it means. Okay, impact except the manganese luminescent center. That is the point. When field is reversed, trapped electrons at the phosphor insulator surface repeat their behavior in the opposite direction. So, in spite of high brightness, the stability of device is good. And AC powder electroluminescent devices, AC thin film, both are high field electroluminescent devices. Technology is different. Powder, there is a thick layer, emissive layer. That thick means tens of micrometer. And powder, lower electric field, 10 power 4 volt per centimeter. Gradual increase of brightness with voltage. Here, in thin film, you have to apply 10 power 6 volt per centimeter. There is a threshold behavior. There is a Zener breakdown. Phosphor layer experiences Zener breakdown. When an electron is injected by tunneling into this layer, then there is a nonlinear increase in brightness with voltage. Then the sharp nonlinear brightness voltage characteristic curve, that is what is making AC thin film electroluminescent displays better than powder electroluminescent display. Okay, we go to next one. This is the structure. You can have a look. There is a substrate. Usually, substrate is a ITO coated glass. It can be plastic or wire also. Okay, and then you have electrodes. Electrodes are usually indium tin oxide for here and anode, and here aluminum usually. Aluminum layer, aluminum electrode, thin indium oxide on the bottom. And you can see insulator both sides and in between the electroluminescent phosphors. Okay, insulator. So why insulator? Insulator is trying to, otherwise the electrical breakdown of the phosphor can occur, damage can occur. So insulator is like a protecting thing, the phosphor. So electric field first goes to insulator, then electron is injected into phosphor. So here different phosphor which are used is, I mean, this is current development. Around 2000, still zinc sulfide is continuing, but some change is there. Zinc sulfide manganese is still continuing. Zinc sulfide copper as a green emitter is continuing. While strontium sulfide doped phosphor, EL phosphor. These are all electroluminescent phosphor. So EL devices. They are phosphor for EL devices. There are other reports. I mean, this is what commercially I have got from a report. And this you can see, same thing. So whatever I have shown here, you can see in this way. Substrate, that is glass or let us say electrode A, then dielectric, then phosphor binder, dielectric, and then dielectric is shielding phosphor from high voltage breakdown. The electrode and light emission is here. What are the different operations? It is given here. See, electric field, then injection, that is injection of electron. Then phosphor electrons are coming to conduction and accelerating, and they are hitting luminescent center. Luminescent center, and then they emit light, and light is coming out. This is the structure. I mean, principal impact ionization, high voltage. And these are some of the other phosphors. Calcium sulfide europium, this is red, with zinc sulfide manganese, and zinc sulfide terbium fluorine green, strontium sulfide cerium blue green, and there are reports, different work, research work they have reported this phosphorus characteristic. This is a composite phosphor, which maybe will be good for white light emitting devices. Zinc sulfide manganese, strontium sulfide cerium. And then this curve, emission curve, EL intensity versus wavelength for zinc sulfide manganese 2+. You can see the orange yellow, around 580 or 590, orange color, you can see orange yellow. And then this was calcium sulfide europium, you can see it is a red thing. You can see this 650, around 650 red. This is around, see this one is a blue, strontium sulfide cerium. Okay, this is blue green, this one, this color around 500 is blue green. And then we go to calcium, gallium sulfide cerium. This is a recent report, last 10 years. This is a blue phosphor, kind of blue emitting phosphor, alternate phosphor, we are trying. Then ACEL devices have some advantages and disadvantages, low wattage, long life. Why I am giving only ACEL devices? As on today for display devices, this is the prominent technology up to even now 2020. Other technology are all, I mean, they are not studying much because of many problems. Okay, low voltage, long life, no external circuitry required, no ballast required to limit current. It can be plugged directly into AC power. It can be manufactured in flat and flexible I mean, they are not affected by temperature, range, and environment because impact ionization is independent of external conditions. That is why. Okay, and then are you able to hear? Not practical for general lighting. It is luminous intensity is not very high, like so. It is you cannot use it for room lighting a room. And poor lumen means light intensity per watt, lumen per watt. 1 watt of power, how much light is emitted? And then flexible sheets wear out, and okay, there are some lamps and high voltage is used. Electricity consumption is more. Okay, we go to next. This is simple LED. LED, whatever LED means, you give electrical current and light is emitted. That is a simple. You can see electron hole depletion region, P type, N type depletion region, light emission, and all that. Okay, we go to next. This is a valence band, conduction band. Electron is going to conduction band, then recombines, comes back with the hole, and light is emitted. This energy is emitted as light. The band gap energy. DC electron. And OLED, organic light emitting diode, is basically a DC electroluminescence. And one of the organic light, one example, PEDOT, these are recent, last 10 years. PEDOT is polyethylene dioxide diophy and conducting polymer. And the TPD is the UI electroluminescent phosphor. TPD, I will diophy. Okay, I will explain this in next slide. Basically, same principle, electron hole recombination. You have glass support, conducting layer, indium tin oxide, that is electrode, then hole injection layer, and phosphor, then electroluminescence. Go to next one. AC electroluminescence. Same thing in another diagram. Polyvinyl here. Phosphor is esters based on binder is ester based on polyvinyl. Just the general example. Typical commercial display device operated with square wave excitation at 200 volt. Pulse width varies from 10 to 50 microsecond. Refreshing rates 60 to 500 hertz. Increase in pulse width increase the duty factor, brightness. Device is sealed to protect moisture and contamination. Okay, solid state lighting is not the part of this talk. As I mentioned, in solid state lighting, you have a UV LED or blue LED. There the principle is here. And then this energy is absorbed by a phosphor, one phosphor or combination of phosphor, and that gives white light. That is the principle of solid state lighting. It involves electroluminescence and photoluminescence. A lot of advantages. Nobel Prize, they have got blue LED discovery, got Nobel Prize. Solid state lighting is all over the world, very popular. And this is the kind of efficiency for LED, semiconductor LED, this is organic LED. Okay, they are telling 2020 they will increase the light candle luminous intensity. Luminous intensity, that is candela actually. I mean the solid angle, one steradian, one candela like that. DC electroluminescence, DC driven mode for OLED, DC driven mode cannot be used because there are limitations. Unidirectional DC flow leads to unfavorable charge accumulation. And excess current will be accumulating, overheating. Lifetime will be reduced. Power losses are there. So power converters will be there. Consequently, AC-driven EL devices only are important for display purposes. AC-driven EL devices do not require costly switching mechanism. Additionally, okay, complicated back-end electronics in driving circuit. So energy saving and cost effective. Then you have thin film and powder, high temperature, screen printing. Thin film you can high temperature, high vacuum, costly equipment. The procedure is complicated. Here it is simple. Offers a powder electron. Some of the powder electron materials, zinc sulfide, zinc gallium oxide, bismuth phosphide, calcium tungstate. And these are the devices done in BRC, chemistry division BRC. Zinc sulfide, copper, ACEL devices. See copper, you can see the blue one, and then the emission is a large area displays. They have done this around 2015-16, large area displays, and is a blue display. Then copper manganese, the color changes there, you can see. And then you have zinc gallate, blue emitting phosphor. Because there is still a demand for good blue emitting EL phosphor, this work was done. This is reported. And the zinc gallate manganese, the studies. While you study the photoluminescence also, electroluminescence also. There can be slight difference. And this is EL device fabricated with zinc gallate. Okay. Then the impact induced luminescence. Okay. These are all high, as I told, high energy electron heating how the with voltage, how the emission changes. That it is mentioning intensity, peak intensity, emission peak intensity versus wavelength. And then strontium stannate and bismuth phosphate doped with europium 3 plus or 2 plus. Europium 3 plus will give you always red color. 2 plus can give blue or green. Here it is blue color. Okay. This is 10 micrometer phosphor. It's a study. And then thin film electroluminescent display, flexible displays. You can see tubes and wires. And then you have the structure already I have mentioned. This is a cross section of actual device. Glass substrate thickness and all. This is 1 millimeter, 1 micron, dielectric layers, and then electrodes, and then material. That is electroluminescent material. Okay. This is viewing direction. Now EL versus LCD. If you see LCD display, you have LCD TV. Now I am coming to LCD display. Let us say TV. Or a simple computer monitor. Let us say is EL monitor and LCD monitor. EL monitor advantage is low wattage, long life. No external circuitry required. It can be made in flexible and all that. But LCD cost is very less. So nowadays these are around 2000. Nowadays people prefer LCD only. This particular report is 2002 or something. Well, disadvantage by EL, poor lumen per watting, very important. I mean, intensity is not good enough. Uniform intensity is not there. Okay. And lot of voltage is used, power usage. Okay. And then this is the structure of AC thin film, same thing in different way. This is silicon over this glass as substrate. Okay. And already I have mentioned this. The process in AC electroluminescence, injection, large voltage applied, phosphor field at the cathode, phosphor interface surface is large, very large field is there. Trapped interface state electron or tunnel emitted into phosphor. Means that insulator is protecting the phosphor. Then it is tunnel emitted into phosphor. Electron injected to phosphor conduction band. If it goes to conduction band, gain energy. When electric field energy, they high velocity. Then transfers. Then it hits the luminescent. That is whatever is that, like copper or manganese, that luminescent ion, dope and ion. And it emits light. And the radiative recombination leads to light. And then the electrons, okay. Then interface state, some electrons can be there. Okay. Then optical outcoupling. Whatever light is emitted has to be coupled. Okay. And then this is TFEL versus LCD. 2002, let us say it is 2002 slides. EL, you see, temperature, it can stand more temperature, higher temperature compared to LCD. And the viewing angle also, these are all 2002-3, because nowadays EL monitors are very rare. EL lamps are there, displays are there, monitors are few. This is one of the EL display, EL technology. Then we come to OLED, which is specific, as I mentioned already, that is the technology which is used for television, transmit television thing. And the mechanism is EL, as you know. And the TV, computer, and mobile phones. All of us using our mobile phone, computer, TV, they are either OLED or LCD. OLED, organic light emitting diode, principally electroluminescence. And LCDs require a backlight because LCD cannot emit. What happens in LCD? You have a backlight, which that light is modulated by the liquid crystal because you use a pneumatic liquid crystal, which is twisted. When you pass current, it becomes straight and allows. So that is the principle of LCD. They are modulating the emission of a source light. In OLED, there is no source light. OLED itself emits light. It is an emissive layer. While LCD is a light modulating device. Okay, so always light modulating device, the dark contrast ratio will not be as good as OLED. Emitting source always will have a means. When light is emitted, it is full. When light is not emitted, it is zero dark. While in LCD, there will be some small current, even when light is switched off condition. So the dark contrast will not be that good as OLED. OLED is having the best contrast. Okay, this is a design. Again, it is the same thing as OLED, cathode. Then in between your OLED organic molecule is there. Then substrate. Substrate is glass or something. And then here light emission is here. Okay. Voltage. Cathode is a metal, usually, magnesium aluminum alloy. Okay. Anode is indium tin oxide only all the time. Okay. Then thickness of organic layer is around 150 nanometer, 100 to 150 nanometer, organic OLED material. Then the band gap of the organic molecule, that is the energy difference between the valence band, highest occupied orbital and the lowest unoccupied orbital. The energy difference is the band gap of that decides the emitted light. The band gap will decide what color light will be emitted. There are two types of OLED: small molecule polymer OLED. The OLED material should have high luminescence quantum yield. High luminescence quantum yield means what is quantum yield? Suppose 100 photons are observed. How much photons are emitted? It is observing energy 100 photons. How many photons are emitted? That ratio. The quantum yield 100 means 1 photon observed, 1 photon emitted. Quantum yield 0.5 means 1 photon emitted, 0.5. 1 photon observed, 0.5 emitted. That is the meaning of quantum yield. And good carrier mobility, N and P type. Good film forming. Actually, thin film means film forming properties should be there. The thermal and oxidative stability should be good, and purity should be good. This is a very important factor. Purity. That's why cost of OLED device is very high, because the purity is very important. The technology for preparing the organic OLED material, that is very costly. That is why their cost was very high initially. Now it has come to some comparable level with LCD. Then okay, I go to next one. I think history I quickly passed through. First OLED device, Kodak company, Tang and Vance like, they had 1987. They had two layer fluorescence, TPD and aluminum. See, TPD diphenyl bismethyl phenyl biphenyl diamine. ALQ is tris 8 hydroxyquinoline. I won't be able to expand it. So I just use that. And light is due to recombination of singlet exciton. Means it is a okay. It is a fluorescence singlet exciton. I will come to next diagram. Here quantum efficiency is 25%. Means 100% energy observed, only 25% emitted as light. The intensity at 10 voltage of this OLED is 1000 candela per meter square. Candela is a unit of intensity. Then phosphorescent materials are also used, where all excitons can be converted into emissive triplet states through inter-system classing. So whenever you use second generation, that is phosphorescent material, you can get very close to 100% efficiency, quantum yield or quantum efficiency. The presence of then heavy atoms like iridium and platinum, if it is present in the complex, which that OLED material, that will increase the spin orbit coupling and fast inter-system crossing will happen, and triplet transition will increase. Highly efficient green and red emitters where 100% quantum efficiency can be achieved. Phosphorescent emitter. Okay. Finally, this is using iridium phenyl pyridine. They have observed 70 lumen per watt. This is 2001 report. And then I already, luminescence means emission of light by a solid, that you know very well. Now, luminescence, photoluminescence, emission of light, it can be fluorescence or phosphorescence. This also, I think, all of you know. I just want to, what do you call, passing mention, I will mention. Fluorescence means, I will tell you. See, let us say this is a molecule ground state. It absorbs energy, it goes to excited state. And normally, singlet excited spin, suppose this is a ground state. Ground state, as Wundt's rule, they have to have opposite spin. Excited state, when it goes, this goes like this. This is called singlet state. And then if the spin is reversed, it requires more energy, that is called triplet state. Now, if you see that, ground state is here, this is singlet state. And triplet state is here, where spin is reversed. Normally, from triplet, you cannot come to ground state because the selection rules for the emission forbid that. Triplet to singlet transition is not allowed. So, it takes more time. And first singlet to triplet energy inter-system crossing. This is called inter-system crossing. If organic molecule is only fluorescent, you will get only 25% quantum yield. If you can see that it populates the triplet state, then you can achieve 100% quantum yield. Then quantum yield of a fluorophore is number of emitted photon by number of observed photon. Quantum efficiency, when you talk, number of converted electron by number of incident photon. Okay, and OLED materials. Okay, conventional polymer, 5 conjugated polymer. They are all low cost. Okay, better thermal stability and all the compounds. Then polyvinyl carbazole was the earliest one which studied, 75-76. The electroluminescence from this was studied. Okay, this is the first structure. Tang and Vance like heterojunction OLED. Whatever device they fabricated in 87, this is the structure. You have two composite material, ITO and magnesium electrode and glass substrate. These two materials together they are used as a OLED emitting system. Okay. The noble metal, when you add the complexes with iridium and platinum, organic complexes with iridium, platinum, and ruthenium, then it is found that the molecules can be taken to triplet state, and then from triplet state, when it comes to ground level, one is able to get 100% contact efficiency and better yield and better brightness. The 25% means you lose a lot of light. You should not lose the light in OLED. So always you should do something to get 100% contact, whatever is possible, best possible. So to date, to open the iridium poly, okay, PPY in this particular thing, CBP is very classic doping system. And these are studies on OLED. I will just tell about one system. Blue, green, this one. Host material, two molecules are there, host and gust. What is gust? See, host energy observed, it goes to singlet state. Then it comes back, I get only 25%. So I take a gust molecule, which is very close. Energy is this single is energy level, and this one very close. So it takes energy and then takes, when it is thermally, it is able to pass on to triplet state of this molecule, post gust. So you get a better quantum post gust. Okay, inter-system crossing and all. You have two molecules. Okay, and then this energy transfer from host to gust. See, this is gust. Okay, S1 T1. This is gust. This process is helping to go to triplet state. Either it has to go from S1 singlet to S1 triplet, or T1 of the gust to T1 of the host. Okay, dexter is a dexter energy transfer, and the other two ways of energy transfer. Dexter and hoster. Dexter means they are very near. Both molecules are very close. So they are just, I pass on to you, you pass on to that person. First, the molecules are away, host plus molecule, but coulombic interaction happens between host exciton and the dopant, which is slightly away. It's a fast exchange. What is exciton for newcomers? Suppose a semiconductor, you pass current, you get one electron and hole. Hole in the valence band and electron in the conduction band. These together, they are called exciton. A pair of hole and electron means it is still in the conduction band. It is not free. That is called exciton. Okay. And then these are the different color emitting. I am giving one set, which is reported for deep red, platinum octothiol porphyrin, green tris 2-phenyl pyridine iridium complex, and this blue, this one. This is recent only, last 3-4 years, it may be 3 years or 4 years before report. Okay. In India, we have group in NIT Rourkela and NPL New Delhi doing somewhat good work. I will talk about recent. I have to give the trends. These blue and highly emitting iridium complexes, but the efficient photo reaction, yellow luminescent iridium complexes. You see chemical structure are complex, and then they make this is the kind of emission. You see blue emission. Because electroluminescent blue emission problem is there. No, this particular complex is emitting blue. Okay, it is talking about yellow. Okay, it's blue. I mean, diagram is not matched, I think. Okay, and here it is 500. It is also blue. Okay, device structure. Always any report they give the emission spectra, device structure, and the results, quantum yield and external quantum efficiency, luminosity, everything. Highly efficient green. This is green emission. You can see this green is around 540, so 540 nanometer. So it is like that. This is absorption spectra, this is emission spectra. Different, they fabricate the cell and measure the thing. Here they are using many molecules. You see, this, let us say this host molecule, they select 1, 2, 3, all are very close. So it passes to this passes, they finally just to go back to host to singlet state, like that. Okay, complex emitter. And then in India, NIT Rourkela has, one Professor Dr. Shivakumar is there. He is doing very good work. And he has published half a dozen papers on OLED emitting materials. This is one of his papers. He has used TPA imidazole derivative for green, as the green emitter. And this is a blue emitter, imidazole, TPA combination, TPA imidazole derivative. These are all published in very good journals, Chemistry Select, and this chemistry, Journal of Photochemistry and Photobiology. And this structure, you see so many things are used. They are all sensitizers. Basically, fluorescence, this triplet state population, they are using so many material which are having this very close energy level. Like from here to here, I showed my earlier diagram. This like substructure, that's what is done in this. Then phosphorescence finally. This is host gust. stress mechanisms. This is a band gap, and you have to design. This is a design of molecule in the research. And organic layers are usually applied to substrate using some other methods. Actually, this is a separate topic. I cannot talk much. Evaporation, shadow masking, inkjet plating, organic phase, vapor phase deposition, the other techniques, molecular beam, epitaxy, there are many things. Manufacturing technology is very costly and very low material is used. That is the reason why OLED is costly. Low material utilization, 5% only. That is why it is costly. The color generation, different approaches are there. Red, green, blue, white emitter and color filter, blue emitter and color converters, and all that. OLED in LCD TV, OLED greater view angle, 180 degree. What is view means? In a room, one person sits here, one person sits here, you should see the same image, 180 degree. That is what, I mean, semicircle you say. This side, middle, all should say same image. That is what is viewing angle. This is very good for OLED. Contrast is very high because it is emitting. I mean, the electroluminescence emitter, substance is emitter. In LCD, liquid crystal layer is only modulator. We use a backlight as a light source. And then temperature, one slightly LCD is better than OLED. The truth is, OLED TV's lifetime is predicted as only 5 years maximum. While LCD is 7-8 years. It is, they have found out, actually. OLED, when discovery itself is only 6-7 years. Its lifetime is estimated to be 5 years. Okay. Then OLED shutters 20180. LG OLED, they have made 88-inch 8K. 8K connects to the resolution of the display. And then 48-inch smallest 4K OLED, 20 years made, 2020. And now intensity of OLED panel efficiency is increased. 190 lumen per watt is very good. Anything above 100 lumen per watt is good. Intensity per power per watt is power. Then latest 2020 OLED, thin film transistor driven full color or OLED. OLED driven by thin film transistor. That is driving voltage with vertically stacked lecture. This is a special structure. That has been developed using photolithography. They have shown high resolution displays of more than 2000 pixels per inch. This is the latest report. Choi et al. Nature Communication. This vertical stacking, photolithography, and new techniques. The details are given in this paper. I go to next one. Carbon nanotubes. The earlier speaker, professor, has explained extremely well. You know about that. They are allotropes of carbon nanomaterial. They have extraordinary strength, unique electrical properties. And now there are devices now, carbon-based single electron transistors. They are very small compared to silicon device. So that's why carbon dot-based single electron transistor is excellent. You are able to see? Are you able to see? The carbon nanotube discovered in
Yes, sir. Yes, sir. Yes, sir. Please go ahead.
Carbon nanotube chips, smaller, faster, more efficient, generate very less heat compared to silicon chips. They are electron emitters in a field effective display device. This is one report. And then there is CNT-based transistor architecture that can drive a OLED at low operating voltage. And this has been reported. And as you can see, this should replace silicon because it's small size. They are supposed to outperform silicon-based CMOS technology. But till now, no breakthrough is there. Okay, that's what is the truth. They are all in lab stage. And CNT future, okay. Zhao et al. 2019. CNT thin film transistor driving flexible light emitting OLED. AM OLED. Active matrix is drive. It tells something about driving voltage. That is this one, TFT. By improving the formation of uniform CNT, they are developing new pre-treatment technique. They have got a better thing. Okay. It has uniform brightness is a report. And for 99.93 yield and all. Okay. The panel driven by high purity semiconducting, promising strategy. It is strategy. Still, it has not come. This is what they have reported in lab scale. And then 1985, there's a report. Thana et al. Is the old one. Okay. High purity zinc sulfide. Okay, 85. Let us not bother much. DMOS, especially this one. Okay, metal oxide FPT. And the AC driven EL devices, inorganic, is a very important review. Those who are interested in electroluminescence work, please see this. Advanced Optical Material 2019. It is a Hall of Fame article. Hall of Fame article, I think you know. It means it is a topmost article. The unique here, they say significant prospects while this EL flexible energy efficient. Electroluminescent devices have flexible energy efficient displays. They can be used to flexible display. They can be used for wire, tape, and cloth, many things. They are all already developed. Last 2-3 years, you can see flexible cloth display, wire display, tape display, and all that. And remarkable progress achieved for lowering driving voltage, enhancing brightness, power efficiency of AC-driven EL devices. Fabrication techniques have changed. That's why. And then large area flexible AC developed, and a polymer dielectrics are used. And the nanowire and many things, many good things are there. They are commercially available. The waterproof and soluble device also have been achieved. And then in our, okay, this much only. Two recent strategies for the EL. First, enhancing effective electric field by using dielectric material. Means electric field should be enhanced using proper dielectric material, flexible or otherwise. The second is improve the efficiency of creation of excisions through balancing number of charge carriers. These are the two strategies. And the high performance multi-functional light emitting sources. Okay, operation under frequent reversal field, they are advantages. Direct integration, these are all known actually. Okay, without incurring power losses and all that. And DC operated. Now, nothing I talked about development on DC. There are 1 or 2 reports. DC operated thin film electromagnetic device. Improved version. I will be finished in 5 minutes. Another 5 minutes I will finish. An improved version of DC operated thin film electromagnetic device is proposed. This is in 1995, which relies heavily on nature of trapping states on P silicon zinc sulfide manganese heterodiode. 95 report. After that, nothing is there. The proposed structure is reverse biased P silicon zinc sulfide grown in argon oxygen and yttrium oxide zinc sulfide. These are the composite actually. Argon H2S grown and there's a transparent electrode. Okay. And then low voltage, this is a recent one. Low voltage DC electroluminescent device using semiconductive band barriers with copper oxide. This is a Japanese report. No other report is there. Where they have done the reduction of driving voltage. They have done while maintaining stability. Driving voltage was reduced using P copper oxide thick film with high performance electrical properties for the formation of 2 semiconductive band barriers in series. It was achieved. N zinc oxide, P copper oxide, controlled current. And P copper oxide, N zinc manganese generated hot electron. Hot electron means high energy field electrons. And high field, whatever high energy electrons are generated, they are hot electrons. Then driving voltage was divided. 98% was applied to hot electron generation. The electroluminescence obtained in 20 volt. That is most important. 20 volt. Okay. Luminescence was insufficient. Means still more work has to be done. That is the report. Okay. And the electroemissive quantum dot LED TV. That is, you can see right now quantum dot TV, the LED TVs are available commercially. What are they? They are nothing but LCD TV, LED LCD TV. You have a blue LED as the light source. They apply a quantum dot layer above that. The quantum dot converts into LED into different colors. So you get a color gamut in the LCD. LCD normally that backlight light is only modulated. So accordingly, using color filters, you generate colors. Using quantum dot, you can have a large color range. So quantum dot layer for the backlight source. That is what is called, as on today, quantum dot LED TV. But now work is going on. Last 2 years, quantum dot emissive electroluminescent TV, a display or TV. Okay, but work is going on, and there is a question mark. One reviewer has told we don't know whether it will come. Okay, perovskite quantum dots for white light emitting. Right now they have prepared perovskite quantum dot using white light emitting for white light emitting diode. Using perovskite quantum dot, they have prepared a white light emitting diode, and then hybrid quantum dot with no buffer layer was achieved. Hybrid means mixer. Okay, this is one report. White emission, these IRID OLEDs present a maximum luminescence and current efficiency. This is micro machines, 2019. Red quantum dots. Okay, and then cadmium selenide hazardous. Recent quantum devices use indium phosphide. Researchers, cadmium selenium is the earliest report on quantum dot. Nowadays it is hazardous, so it is not used. They use indium phosphide and other modifications, and also cadmium-free material, including graphene and perovskite. But all these works are in the earlier stages. This is what is proposed. Quantum dot emissive ELTV. See, this is a cathode, then quantum dot layer, which will directly emit light. and it will absorb the electrical energy and emit light, and that will go through anode and display. This is what is proposed. Till now, it is not done. Okay, I think I have come to the end. So just we remember Dr. Abdul Kalam, our ex-president, courage to think differently, courage to invent, courage to travel the unexplored path, courage to discover the impossible, courage to conquer the problems and succeed are great qualities of young mind, young India. This is what our ex-president expecting from young minds. And then this is for a general audience and my favorite poem, but he is not well known, this poet. This is a story I was told by a wise man that is very old. Success is not just reaching the top, but also helping others go up. Success is not about showing you are superior, but helping others know that they are not inferior. Success is about making people smile, helping others live a life that is worthwhile. And these are the funding agencies for research in our India. Just I am giving the names. And thanks a lot for a very patient listening. Thank you. Usha, thank you. We close. Gautanga.
Thank you, sir. Thank you very much. Thank you for your informative and intellectual. Kokode sir, will you please take the charge?
Yes. Thank you very much, Natarajan sir. Very expert, that is a talk and very elaborative talk that you have given on the recent trends in electroluminescent devices. Now the session is wide open for any questions from the participant. Any question? Natarajan, sir, there are some questions from the chat box. I will, 2 or 3 questions I will take. Natarajan, sir, the first question is, why ACEL method is more prominent method than others? Please explain along with efficiency.
Hello, Natarajan sir. Please unmute yourself.
In DC operation, if you want brightness, you have to increase the current. Whenever, if you keep on repeatedly increasing current, the material is damaged fast, lifetime is less. While in AC operations, because of the reversal in the voltage, the material is not damaged. Not only that, the principle is impact ionization. Okay, and you have insulating layer and other things. So the device lifetime is increased. So AC is better all the time. And DC you have to convert into AC when you want to use. So you have to include that in the circuit and all that.
In terms of efficiency, sir?
Efficiency, but instead of efficiency, we have to see, of course, light efficiency is possible only with AC TFT, thin film electroluminescence. They are the only way of getting best stable and efficient devices. DC we used only for lamps. DC power supply used only for lamp displays, small displays, packet displays.
Sir, another question is there. What is up next? OLED.
Yeah. Okay.
What technology is going to come after OLED?
That's what I told in the last slide. I don't know whether you missed it. Quantum dot LED is the thing. Means quantum dot as a emitting layer, emitting material. You can have an inorganic quantum dots, or you can have a mixture of inorganic and organic hybrid quantum dot, which will be the emitting substance. So it will be called quantum dot ELTV, QD-ELTV. That is the technology. And currently only that much. Nothing else is, people think is finally it has to be profitable. So people don't put money if it is not profitable. We have to see whether carbon dot will be useful for display purposes. They have used carbon dot in as a driver voltage purposes. Okay, like they have used TFTs and other. So as on today, OLED has taken the market. 10% of Indian market is OLED. World market also. 90% is still LCD. OLED, flexible OLEDs is one, which is now being, which is coming. Flexible EL devices is one. And last technology is quantum dot emitting ELT. That we see will be coming in the next few years. Flexible things are available right now only. Flexible EL and flexible YL. This is what I can say. Future more than this, I cannot predict. Only one thing I can say is success in lab doesn't lead to success in commercial market always. For example, 34-inch EL TV was produced by Hi-Fair company US in 2003, but they could not bring it to commercial market because by the time they produced some 100 pieces, the cost of LCD fell down by a factor of 10. So they could not bring it to market. So commercially, there are many things which we cannot predict. Only thing I can say is carbon dot may help in some way, and quantum dots will help in having new technology. Okay.
Sir, there is a last question. Some of the participant is asking that you have mentioned electroluminescent materials, hybrid materials. So
hybrid.
What do you mean by the hybrid materials?
Hybrid means one inorganic, one organic, one layer of inorganic, one layer of organic. That's what mean. Inorganic, organic hybrid. Yes. Okay, it is separate, but they in the layer, one layer, two layer will be there, like that. Hybrid. Like perovskite and some organic layer. Actually, I have not read 20 reports in detail. There are reports. If anybody wants, they can write. I will send them the particular paper. They can go through that. Okay, my email they have to take. v.natrad.yahoo.co.in. I'll send them the particular paper because about half a dozen papers are available on this topic. But they are all in the lab scale only. Nothing but poor device characteristics and all that. Okay, they have not come to. We have not asked the lab.
Okay. Okay. Thank you, sir. Thank you very much.
My email is v.natrad.yahoo.co.in. I think anybody who wants any specific reference, please write to me. I will get it and forward it so that you can do further. Any researcher who is interested. Okay.
Okay, sir. There is no further question. So I thank you very much for the very nice presentation, very nice talk, very good deliberations, and you have explained some of the queries also. So on behalf of the organizing team, I thank you very much. Thank you, sir. Over to the.
I also thank you for giving me an opportunity. You and other Dr. Karthik Shinde management for giving me an opportunity to talk to this audience, big audience. And I'll be happy to receive the feedback from the audience in my WhatsApp. Whoever wants, some feedback, any specific questions, anything is there, I will answer. Thank you very much.
Thank you. Thank you, sir.
Thank you.
Over to the Egao person.
Now on the sir. Once again, on the department on the behalf Department of Physics, I also very thankful respected Dr. A.S. Kokode sir, Principal of the Evazabai Hitkati College, Brahmapuri, for conducting this session. Thank you very much, sir. Now, our webinar is in the last stage, that is the thank session. So, thankful is the beginning of the gratitude, and the gratitude is the completion of the happiness. So, for this validated function, I invite Dr. Kuldeep Bhongre sir for the vote of thanks.
Okay, sir. So I am audible, sir.
Audible.
Good afternoon, everyone. I am honored and lucky to have an opportunity to give a vote of thanks on this special day. So for the today's international webinar, more than 500 participants of various colleges and universities from all around the globe are registered. So this is a huge success in itself. I want to thank State Dr. Vivek Joint Secretary Bhadravati for encouraging us to do more knowledge-sharing events like international webinar. On my own behalf, a very hearty big thank you to Elias Element sir from Nigeria for his effort toward the topic through new dream, but not from old source, the case of the carbon dots. I especially want to mention the synthesis as well as grouping of the carbon dots part that we just explained in very detailed and wonderful way. Thank you, sir. I must mention our deep sense of appreciation for Dr. V. Natarajan, sir, ex-scientist, DRC Mumbai, for his explanation of recently released electroluminescence devices, in which he explained the subject was extraordinary. Thank you, sir. I would like to thank our beloved Dr. N.S. Kokode, sir, Principal, NH College, Brahmapuri, and Dr. Ishwar Murle, sir, Registrar, Gulbarga University, Kadcholi, for accepting our request for the chairperson for today's webinar. Finally, I again want to thank respected Sri Nikhatravi Shinde Sahib, Dr. L.S. Ledley, sir, who always encourages us for organizing such event. I also want to thank to a person behind this event idea, our organizing secretary of this webinar, Dr. Karthik Shinde, sir, and convener of this international webinar, Dr. A.D. Dalinagar, sir, and Dr. G.R. Bekri, sir. I also thank you to all the participants in this international webinar, without which this event is not completed. I would like to thank organizing team members, technical team members, Pradhan sir, Vaibhav, and other staff members of the college. I thank organizing
So, thank you, Ladke sir.
Thank you.
Ladke
धन्यवाद.
sir. Thank you very much. Dr. Karthik Shinde and Begavkar sir, Bedre sir. हरणे सर नाही दिसत.
हरणे सर तिकडे बसले आहेत दुसऱ्या रूममध्ये.
होते मॅडम दिसल्या मध्ये. व्हेरी नाईस.
थँक्यू सर, थँक्यू सर, थँक्यू फॉर युअर कोऑपरेशन. तुम्ही असले की आम्हाला जोर येतो आहे. तुम्ही पाठीशी असले की सगळं काही व्यवस्थित होतं.
थँक्यू. कॉंग्रॅच्युलेशन्स NS शिंदे कॉलेज.
Thank you, sir.
Thank you, Natarajan sir. For your nice expert speech and knowledgeable speech.
Hello.
Namaskar, Kokode sir.
Please stand up for the national anthem. I request all the participants. Thank you all. Thank you for your actively participation. Thanks.
Gautam?